Hi guys, it's Sydney. Today we're doing Big Idea 6, Equilibrium. So sit down, get yourself a nice hot chocolate, maybe a snack, because it's going to be a long one. Are you ready to learn? Let's go.
Okay. With equilibrium, this is the last of 6 big ideas, and so this encompasses all of equilibrium, all the way from general equilibrium to acids and bases to Ksp. So just a quick reminder of what is equilibrium. So equilibrium is where your forward rate and your reverse rate are equal. The rate of your forward reaction and the rate of your reverse reaction are equal and constant, so there's no changing the reaction rates once you've hit equilibrium. And that kind of is explained by these 2 graphs down here, which shows you start with a lot of reactants, you start with no products, and over time you use up your reactants, which slows down your rate. You make more products, which increases the rate of product formation until you hit equilibrium, and then notice over time the rates stay constant. This shows you your calculation of Kc, and so what does this little c stand for down here? Concentration, which means your products and your reactants have to be given in concentrations. If it's Kp, make sure you show pressures. What is not included in any equilibrium constant expression? Units. Oh yeah, units and solids and liquids. So K does not have solids, liquids, or units. And so the next thing we're going to look at is manipulating Q and K. So remember, Q is an equilibrium constant. You have to be at equilibrium in order to give a value of K. Q is the reaction quotient, which is just the progress of the reaction over time. And so do you have more products, do you have more reactants, or are they equal? And then Q and K, again, only include gases and aqueous solutions, no solids or liquids. And then down here, this little chart shows what we talked about in class, kind of like with Hess's law. If you have to flip the reaction, you actually take the inverse of K, so you would do 1 over. If you multiply a reaction by 2, you would square the K value, and then if you add 2 reactions together, you actually multiply the equilibrium constants together in order to get the overall value of K. And then with kinetics and equilibrium, so the biggest thing with this is that kinetics only looks at the reaction rates, where equilibrium tells us the progress of the reaction. Kinetics has a K as well, but it's lowercase and has units. Equilibrium constant is a capital K and has no units. And if your reactions are unequal, that means you are not at equilibrium. You are not at equilibrium until your faster reaction slows down and your forward and reverse reactions have equal rates. So then Q versus K, this goes along with the Q versus K bars. Looking at Q, that is when you're at any point during a reaction. So if you're like, I'm not sure if I'm at equilibrium or not, calculate Q, because that will tell you what would have to happen for your reaction to get to equilibrium. And so if they're equal, then you're at equilibrium. If they're not equal, then your reaction is going to have to proceed in some direction for your Q to change. My K bars should be the same, but I got a little ahead of myself. So Q is what has to change. K is a constant, and so K will never change. It won't, well, unless you change temperature. But your Q is what's changing. So then calculating K, this now is going to go through some examples of calculating K and calculating concentrations that we didn't look at in class. And so when you calculate the equilibrium constant, you have to use equilibrium concentrations. And so you always want to write an equilibrium expression. If they give you the reaction, use the reaction to write the K expression. If they specify Kp, make sure you write Kp. If they specify Kc, make sure you write Kc. And then look at the equilibrium concentrations or pressures, depending on what you're solving for, and substitute those in to solve. So this says, calculate K for the following if you have 0.198 moles of CO2, 0.0908 moles of H2, you have CO and H2O in a 2-liter container. And so to solve for K, more than likely, let's say this is Kc, it's going to make life easier for us. If this is Kc, that means what do we have to make sure to plug into the K expression? Concentration. So that means make sure if you're given moles that you solve for concentration for each one of these. This says that these are all of your amounts at equilibrium, so we don't have to really even worry about nice table. because they already gave us our equilibrium amounts. We just need to convert to concentration, and then we plug all of our concentrations in to solve for K. Then we can also determine equilibrium constants using an ICE table, and that's if they give us initial amounts and they give us one of the equilibrium amounts. But again, your first step should be writing an equilibrium expression. Always do that even if they don't ask you, because sometimes you get points for doing things like calculating moles and writing your equilibrium expression. And then look at your concentrations, plug them into an ICE table, and then solve for your equilibrium concentrations and plug them into your expression. So this says initially you have NO, H2, and H2O, no N2. So here's your equation. And then at equilibrium, they give you the NO concentration, and it says to determine K. So really, if we look at this ICE table down here, this helps us more. They use X's up here, but we already know what X is, because they gave us initial amounts for everything, and they gave us an equilibrium amount for NO. What you have to make sure that you look at, though, are the coefficients. So the coefficient for NO, H2, and H2O were all 2. So a 2 to 2 ratio is basically what? 1 to 1. And so if we are using up 0.038, because this is a reactant, so that's why it's minus, because your reactants are being used up, you're forming products. So if you're using up 0.038 molar of NO, that's also how much H2, because it's a 1 to 1 ratio. And then you have to cut that in half to find your N2 amount. And then once you have your equilibrium concentrations, you can plug in and you can solve for K. And then you can also calculate equilibrium concentrations if you're given your K. So this is another way that you can calculate the pH of a weak acid. Because to calculate the pH of a weak acid, you would be given the Ka, and then you can solve for the equilibrium concentration of H plus to solve for pH. And so if they give you a K, then always start by writing the equilibrium expression, and then use an ICE table and fill in the initial amounts, determine whatever your changes are. And if you don't know something, use X. And if you don't know something, use X, and then determine the equilibrium values with your X's. So maybe it's 1 minus X, or 0.7 minus X. And then plug everything into your K expression. And then what do you do to make your life easy? Assume X is small, make sure you write that down somewhere, and then you will determine all of your equilibrium amounts by using X. You'll kind of plug everything back in. And so this gives you Cl2 yields 2Cl, and it says determine the equilibrium partial pressures of all species if 0.5 atm of Cl2 is present initially, and they give you your K. So now we're focusing, really, this would be what little subscript could we put down here for K? Kp, because we're dealing in pressures. So, and then they're probably not going to have you convert between Kp and Kc. You used to be given that equation on the formula sheet. You're not given that equation anymore, which means you're probably not going to convert between the two. And so this would be Kp because we're dealing with pressure. And then what we can do is, oh, I thought it was going to be a big picture. What we can do is use an ICE table. So initial change equilibrium, your initial amount of Cl2 is 0.5. You're not going to have any Cl initially, unless it tells you your products are usually going to be 0 initially. And then we would use minus X plus how many X for Cl? 2. So don't forget to take your coefficients into account when you're putting your X's in as well. So we would have 0.5 minus X, and then we would have 2X, and we could plug that in with our K, solve for X, and that would give us our pressures of everything. So then the magnitude of K, so what K means. K really just tells us what we have more of at equilibrium. If K is small, we have more reactants than products. If it's large, we have more products than reactants. If K equals 1, when K equals exactly 1, we are exactly at equilibrium. If K is not 1, then we have slightly more products or slightly more reactants, depending on where it falls in that scale. But when K is exactly 1, we are at equilibrium. If it's less than 1, and by less than 1, remember that means it's like 0.0001. K can't be negative. You'll never have a negative equilibrium constant. It's just going to be either a really big number or a really small number. And so this just shows us the particle diagrams looking at K. So this is the diagram below represents a certain equilibrium position at a certain temperature for H2 plus I2 yields 2HI. H2 is represented by the two lighter circles, I2 the two darker circles, and HI is one of each. What can be said about the equilibrium position in terms of reactants and products and the likely magnitude of K? So what we want to do is we want to compare how many products we have versus how many reactants that we have. So if you look at this particle diagram, what do we have more of in this picture? We have more products. We have more HI because I see a lot more of the one dark, one light circle than the ones that are the same. So if we have more products, that means we can eliminate C and D, and we give ourselves a 50-50 shot. If we have more products, what does that mean about our value of our equilibrium constant? It's large, because when you calculate your equilibrium constant, your products are on the top. And so K is large and products are favored. This would be probably a multiple choice question if they were to ask this, because particle diagrams can very easily be thrown into multiple choice. So Le Chatelier's principle is one way that you can describe changes in equilibrium. In order to use Le Chatelier's principle, you have to make sure that your system was already at equilibrium. So if it says you had a reaction at equilibrium and then you made a disruption, you can use Le Chatelier's principle. So there are really three factors that cause a shift in equilibrium, and that's concentration, pressure, and temperature. And remember, just look at your equation, your balanced equation, as you go through and you look at how the change affects it. Because if you are adding a reactant or a product, that's going to always shift in a way that undoes the change. So if you add a reactant, you now have too many reactants and you're going to shift to make more products. If you add a product, you now have too many products, and so you're going to shift to make more reactants. When it comes to pressure, and I know I talked about this in class as well, but it's always the one aspect that is most missed, because when you change pressure, you only are dealing with gases, because gases are really the only thing that affects pressure. And so when you are changing pressure, you only focus on moles of gas when you're focusing on that change. And so if you're increasing pressure, that means now your pressure is too high, so you have to shift in a way that would bring pressure back down, and so you're going to shift to the side with less moles of gas or less gas molecules. When you're changing temperature, always treat heat as a reactant or a product. And so if something is endothermic, that means heat has to go into the system, and so heat would be a reactant. If you have an exothermic reaction, that means heat is released, and so heat acts as a product. And then what you can do is then just treat increasing temperature means you're adding heat, decreasing temperature means you're taking heat away, and then you just treat it as if you're adding a reactant or a product, or removing a reactant or a product. And so here are some examples. So consider the following equation. You have H2 plus X2 makes H2X plus energy. So if you have this plus energy over on the right side, that would mean that this reaction is what type of process? Exothermic, because you're releasing heat. So this would be an exothermic reaction. So addition of X2 to a system described by the above equilibrium will cause what to happen? So if we add more X2, means we have too much reactant, and what's going to happen to this system? It has to make more products. And so that means that we need to figure out which of these is going to happen. So we're making more products, which means we're using up the excess X2 that we've added, but we're also using up the H2. So as we make more products, we also use up our reactants. And then it says increasing the pressure by decreasing the volume will cause what to happen? So if we increase the pressure, our pressure is now too high. Which way does it have to shift to bring the pressure back down? To the right. Why? Less moles of gas. So we have to shift to the right, which is the side with less moles of gas. So as we shift to the right, we're going to use up our reactants, and we're going to make more products. And then if we increase the temperature, so when we increase the temperature, that's just like us adding more heat, more energy, which is a product. So if we add more product, which way are we going to shift? It's going to shift to the left because we need to use up this excess. And so if we shift to the left, we use up H2X and we make more of the products. And so there's a way that we can experimentally look at Le Chatelier's principle, and that's by using the FESCN equilibrium system. And I can't remember if we looked at this in lab or not. But systems at equilibrium can be examined using Le Chatelier's principle by looking at pH, temperature, and then we can also look at the color of the solutions, which helps tell us the concentration. Another example, and I know we didn't look at this in the lab, but an example is looking at this complex ion. Again, you don't need to worry about what complex ions are, but they might give you an example like this and say that this complex ion of cobalt is normally pink. And then cobalt 4 chloride is normally blue. And so it might ask you a question about, if your solution is more pink, what does that mean at equilibrium? That means you have more reactants. If it's blue at equilibrium, what does that mean? That means you have more products. And so looking at the colors can also tell us where we are at equilibrium. If you see a little bit of pink and a little bit of blue, that means we're probably right at equilibrium because we see both the pink and the blue. So this is the Haber process, is the industrial process that's used to manufacture ammonia. It relies on this equilibrium. It says which of the following will maximize the ammonia formation in the equilibrium mixture. So what can we do to make sure that we have the most ammonia possible? And so it gives us these different scenarios at what we can do. And in order to make more ammonia, we can just add more H2 because H2 is a reactant. And if we add more reactant to this system that's already at equilibrium, it will shift to use that excess up and it will make more product. And so I kind of talked to you guys already about how College Board wants you to look at changes in equilibrium, and one of the ways that you can actually look at changes is by looking at Q. And so remember that Q is at any point in the process. So if a problem just says you add 5 moles of reactant and 2 moles of another reactant, which way will it shift? That means that you want to calculate Q and compare Q to K. So Q gives us a lot of different ways to look at equilibrium. We can look at just a shift in a reaction. Q is also, if you remember when we talked about selective precipitation, and so we compared Q to Ksp to figure out which way a reaction will shift. We always are just comparing where we are at in that point in the reaction with our K. You always have to be able to compare to K. So you have to have K in order to compare. And so this just kind of extends that Le Chatelier's table by, if you add a reactant to something that's already at equilibrium, now you have too much reactants. And if you remember when you calculate Q, it's the same way as K. And so it's always products over reactants. So if you add a reactant, your number in the denominator is now too big, which is going to make Q decrease. And if Q decreases, that means it has to shift to make more products. So you can describe it using Le Chatelier's principle, but you can also describe it using K versus Q. And if it says justify with a calculation, that could mean just calculate Q and compare it to K. So now on to acids and bases. And so when you look at acids and bases, you want to be able to tell if it's a strong acid or a strong base. And one way that you can tell is by looking at a particle diagram. And so if you look at a particle diagram and you have a strong acid, what happens when you put a strong acid into water? Dissociates completely, which means if you're given a particle diagram and asked if it's a strong acid, you should look to see if it's dissociated completely or almost completely, versus a weak acid, which hardly ionizes at all, and it only ionizes 5% at the most, which means a majority of your particle diagram for a weak acid should be mostly molecules with a couple H pluses and A minuses. So then looking at the pH of a weak or of a strong acid. So when it's the pH of a strong acid, when something is strong, it goes to completion. When you have a strong acid or a strong base, it's a single arrow. So if you're looking at HCl breaking up into its ions, it's HCl with a single arrow, H plus and Cl minus, because it ionizes pretty much 100%. A weak acid or a weak base is always at equilibrium. And so we have to then look at equilibrium calculations when we calculate pH. But if we are taking a look at two monoprotic acids, and so here this is a pH of 3, this is a pH of 3. So it says this is a particulate picture or particle diagram of a strong acid. And so if we take a look at this, we can tell this is a strong acid because notice that it gives us kind of the key down here. HA, H2O, and then A minus and H3O plus. And notice majority of this is H3O plus and A minus. So we have a lot of completely dissociated strong acid. Where over here, this is a particle diagram of a weak acid because look at all of these HAs that we have in here. Not much of this is ionized. And so that's the difference between our strong acid and our weak acid. If we want to calculate the pH of this concentration, if this is our concentration of HA, this is also our concentration of H plus because it's ionized 100%. And so all of this concentration is now H plus. So we just take the negative log of our concentration of our strong acid to find pH. A weak acid, though, we have to use a nice table for. And so if this is 1 molar of our weak acid, that's our initial amount of weak acid. We have 0. Well, water doesn't matter. Why doesn't water matter in an ice table? It's a liquid. So we have 1 molar of HA, we have 0 A minus and 0 H3O plus. If we don't know any other information, we use X's. Typically, if you are given Ka and given an initial amount, you'll be using X's. And then we can plug everything in. So we can do 1 minus X, X, and X. Plug everything into our Ka. What do we need to solve for to find pH? H plus. So we use the ice table to find H plus. And then we can find pH by taking the negative log of that. And there was one of the free response questions that was in that packet today that asked you to find the pH of like a 0.75 molar solution of weak acid. And so you just use an ice table when you want to find the pH of a weak acid or of a weak base. Okay, so then looking at titrations, this shows a lot of different titration curves. This titration curve is looking at a weak acid with a strong base. It tells you it's a strong base down here, but we can tell this is a weak acid two different ways. First, pH of 3 is a higher pH, and so that tells us it's a weak acid. But the other way is looking at the equivalence point. We have the pH of 8.8 at the equivalence point. If we have a strong titration, our equivalence point should be what? 7. Like this one up here. But since this is higher, remember, strong always wins. The reason that strong always wins has to do with the salt that is formed, not just that strong always wins. But in this case, so we have a strong base, we have a weak acid, and we also have this buffer region. Notice we don't have this nice little curve in the strong titration. It's like flat, straight, flat. Where when we have weak titrations, we always have these nice buffer region curves. Same thing with here's our weak base and a strong acid because of the pH at the equivalence point. We still have this buffer region initially, and then our pH drops. This shows a polyprotic. So when you see protic, monoprotic meaning 1, diprotic meaning 2, that's just how many H's it has. And so this would show maybe H2SO4 because it shows 2 equivalence points. And so this slide actually has a link to review titration calculations, and so you can go through strong and strong weak calculations, but just a couple like things to remember. Strong titrations is always stoic. You never have equilibrium ice tables in strong because everything goes to completion. So strong titrations is just stoichiometry. It's single arrows. If you have strong weak, strong weak titrations, and that was the day of 45-minute problems over in the fishbowl. That was when you have to do stoichiometry first because you're neutralizing, and then you do equilibrium with ice tables. So strong titrations are just stoichiometry because they go to completion. They're single arrows. Strong weak titrations, you do stoichiometry first for the neutralization because that's a single arrow. Then you do equilibrium with ice tables. Because in a strong weak titration, you have that salt that's formed, and that salt is no longer neutral. And so this was one of the free response questions, I think one that I gave you today, with potassium sorbate, and they gave you the molar mass added as a preservative. And so first it says, write the net ionic equation for the reaction between potassium sorbate and HCl. And so you can write the equation. Remember, if it's an ionic salt, like this, how do I know this is an ionic salt and it's soluble? How do I know it's soluble? It has potassium, right? It has K. And so it's ionic because it's a metal and a polyatomic. It's soluble because it has K. So I would split this up into its ions. And then what about HCl? Would I split HCl up into its ions? Yes. Why? It's a strong acid. Good. And then we would react this like a double replacement. Or if you recognize this is a strong acid, then you will transfer your proton over. But then it asks for net ionic, and then it says that you have a certain amount of HCl required to reach the equivalence point. Calculate the concentration of potassium sorbate in the stock solution. And then they give you pKa's for titrations, and they say the pH at the equivalence point is 2.54. Which of the following would be the best indicator? Justify your answer, and then calculate the pH at the half equivalence point. And then they have you draw the diagram. And so looking at the net ionic equation, we can actually just represent it by using H+, and then the sorbate ion is at equilibrium with sorbic acid. That's because sorbic acid is weak, so we don't break it up. K and Cl are gone because those are spectator ions. They exist in solution on both sides. And then the stock solution, calculating the concentration. So you can use MAVA equals MBVB if you want, or you can find moles of HCl, and that's how many moles of the sorbate ion that you would need. And then you divide it by your volume, which is 45 milliliters. And so 0.832 molar. And notice the way these points are broken down, you get moles of HCl. So even if you're like, I'm not sure what to do here, I know I'm given a concentration and a volume, I can find moles. Notice you still get one of those points just for finding moles. In part C, because your titration results in a pretty low pH at the equivalence point, you probably won't use phenolphthalein, even though a lot of times that's what we do use. We want to find where pH equals pKa for the equivalence point. And so this thymol blue has the pKa closest to the pH. And so it's actually 2 points. One for whatever you're going to use for your indicator, one for your justification. And your justification can be as simple as the pKa is closest to the pH. Right? That's a justification. pH at the half equivalence point. Oh, I read equivalence point. Half equivalence point is much, much easier, right? Because if you remember, the pH at the half equivalence point equals the pKa of the acid. Right? Half equivalence point, pH equals pKa. I read this as equivalence point, and I was like, oh my gosh, that's a long calculation. Half equivalence point, pH equals pKa. They gave you the Ka of the acid. So if you take the Ka of the acid, this lowercase p always just means take the negative log of it. So you just take the negative log and you get your pH. And then E, they wanted you to actually draw the titration curve. And so you started at a high pH. Did it tell you the pH initially?
There was a dot on it, I thought.
So they gave you this dot for where you were ending, and then
They gave you a start.
Oh, that's why. Oh, yeah, they did. Okay. I don't know why So, yeah, starting and ending point, basically. But for this was really just having you show the half equivalence point. I mean, you could have kept going with this because this was actually your equivalence point. So you could have like brought it down and kept going. But they really were just focused on this half equivalence point part. So you started, what they wanted was kind of this curve for the buffer region. Because since this was a weak strong, it should have been curved for the buffer region. So this was 3 points. You should have had this slight curve. You should have marked where the half equivalence point was, and then you wanted it to be fairly steep through the equivalence point. So then looking at Kw and temperature, and we looked at this in class, Kw is on your equation sheet. That's where H plus equals OH minus, and at 25 degrees Celsius, it's 1 times 10 to the negative 14. But the biggest thing with this, and like we talked about in class, is that they do not want you to classify something being neutral as being 7. What they want you to do when you classify something being neutral is saying that H plus equals OH minus. Or that something is acidic, not because the pH is less than 7, but because the H plus concentration is greater than the OH minus concentration. Or if something is basic, it's because OH minus is greater than H plus. So it's just kind of redefining what it means for something to be neutral, and it's just focusing on H plus compared to OH minus. So acids and bases and their pHs. So here's an example question. You have a 25 milliliter sample of HF titrated with 25 milliliters of sodium hydroxide. At the equivalence point, what would the pH be justify with a reaction? So a little bit different now, justifying with a reaction rather than a calculation. And so you are titrating. HF is what kind of acid? It's a weak acid. So you're doing a weak acid, strong base. So where would you expect the pH to be at the equivalence point? Above 7. Right? And so the reason that it's above 7 is because we have water and sodium fluoride being formed at the equivalence point. Sodium fluoride is a salt, but it is not a neutral salt. Instead, you have F minus, which plays a role in pH. And so the equation that they would probably be looking for would be this one down here, which is F minus, which is the conjugate base of HF, reacting with water. Because at the equivalence point, you have the salt and you have water. Sodium is not going to react with water at all because it's neutral, because it comes from a strong base. F minus, though, will interact with water in this equation down here. F minus, when it gets added to H2O, F minus acts as a base, and so it's going to accept a proton, forming HF and OH minus. And so then, looking at pH again, it says vinegar is 0.5 molar with a Ka of 1.8 times 10 to the negative 5th. What would be the pH of this solution? This is an initial amount of acid at equilibrium with its ions. Use an ice table. And so for this ice table, you have the initial amount of 0.5 molar. You have 0 and 0, unless they tell you you have 0 products initially. If you don't know anything else, you're like, all I know is this is how much I have initially, use X's. If they give you an initial concentration and they give you a Ka, you'll be using X's. So we can do minus X plus X plus X. Why do we subtract the reactants? You use up reactants and you make products. And so when you plug everything in then to your Ka expression, notice how they showed the Ka expression. You never know when you get points for that. Assume X is small. See, they did the quadratic. That's silly. Assume X is small. You get the same answer. And then don't forget, when you solve for X, you're actually solving for H plus here. Then take the negative log of that to get pH. And then it says identify and compare the relative strengths of the two acids and two bases in this neutralization reaction. And so when we look at relative strengths of acids and bases, we have to look at how the reaction proceeds. And so first we can look at what our acids, what our acids and what our bases are. And so just look at what happens from left to right. OH minus accepts a proton, it's a base. NH3, if we go from right to left, NH3 accepts a proton. So OH minus and NH3 are our bases. NH4 plus and H2O are the acids. And remember that your reaction will proceed where your stronger base accepts the proton. And so if these are my reactants, and because they're on the left, I'm going to assume that they're the reactants. OH minus is going to be my stronger base. And if this is my stronger base, and this is my weaker base, that means that you always have an acid-base pair. If this is a stronger base, this is the weaker acid. Where's my mouse? There it is. Within an acid-base pair, the stronger the base, the weaker the acid. The stronger the acid, the weaker the base. And so because OH minus acts as my reactant, and it's a base, that's the stronger base. H2O is its conjugate acid, which means H2O is a weak acid compared to NH4+, because NH3 is the weaker base of these two. So if NH3 is the weaker base, that makes NH4+ the stronger acid. Acids and bases and their reactions. So when you're looking at particle diagrams, always, or even when you're looking at word problems, always ask yourself, is it strong or is it weak? And label those. Label if something is a salt. How do you tell something is a salt? If it's an ionic compound, it's going to be a salt. If it's a buffer, so if you have an acid-base, a conjugate acid-base pair, it's going to be a buffer. And then think about what it will do in water. So what I mean by that is it neutral in water? So like Na plus is neutral in water because it comes from NaOH. Where like F minus, like we just looked at, F minus is actually a base because it comes from a weak acid. So F minus is a weak base. And then it says deal with strong acids and bases first because it's just stoichiometry. So everything goes to completion. How to build a buffer, we talked about this in class as well. When you are looking for the pH of a buffer, you're going to look at the pKa of the acid. So if you want an acidic buffer, you're going to have a weak acid and a conjugate base. If you want a basic buffer, you're going to have a weak base and its conjugate acid. But you always look at pH compared to pKa of the acid in the pair. If you want a pH of 5, you want your pKa to be close to 5. The more equal the concentrations, the better, just because then you know for sure that your pH equals your pKa. And then, well, choose a pair that has the pH closest to the pKa. And then buffer capacity, if you remember when we talked about buffer capacity, the higher the concentration, the better. Because the higher the concentration, the more the reaction, or the longer the reaction will take. Because the more concentration, the more reactants you have to actually react and be used up. And so then here is the example of the buffer region, again, in a titration. At the half equivalence point, pH equals pKa, and that's because your weak acid and its conjugate are equal. So at the half equivalence point, pH equals pKa, and acid equals base. Weak acid equals conjugate base. When it comes to buffers, if you remember, what was the equation, what was the buffer equation that we used to calculate pH? We had H plus equals something, and this was the one thing that wasn't on your equation sheet. Do you remember? How do we calculate here? Let me do this first. How do we calculate the Ka of just anything? Very general. Products over reactants, which was H plus times A minus over HA, right? H plus times the conjugate base over the weak acid. How can I rearrange this to solve for H plus? Multiply by HA and divide by A minus. So we get Ka times weak acid over weak base. That's the buffer equation that you guys had to use. So if you have to find the pH of a buffer, that's what you can use. Now you can use the Ka, right? If you're given the Ka of the buffer and you know the concentrations of the acid and the base, you can just solve for Ka and rearrange it yourself. Or just remember H plus equals Ka times acid over base. We didn't use the Henderson equation because that was too complicated and it could possibly change. This never changes. Whether it's an acidic buffer or a basic buffer, this never changes. And so this says a student must create a buffer with a pH of 6.2 from an acid that has a pKa of 6.5.
Patty Gaston, please dial 1010. Patty Gaston, 1010.
And so it says they need to do what? And so in order to create a buffer that has a pH of 6.2, they would need to make sure that the solution has just a little bit less of A minus than HA because our amounts aren't quite equal. And so again, if you remember, pH equals pKa, or when these two things are equal. In order to get these two things equal, we have to even out the acid and the base a little bit because those two numbers right now aren't equal. And so what we have to do is make sure the solution has a little bit more weak base, because then I'm going to be multiplying my Ka by a smaller number to bring the number down to 6.2. So that's why it's A minus instead of HA. And so when we're looking at finding the major species, they like to use the word species in all of their equations. This gives us another example. We have acetic acid titrated to the half equivalence point with NaOH. Which of the following options shows the correct ranking for molarities of the species in the solution? So we're at the half equivalence point. What is true at the half equivalence point? pH equals pKa because your weak acid equals your conjugate base. And so when we look through this, we want to figure out what has our weak acid equaling our conjugate base, and then kind of going from there. Which, if we look at this, we really only have option B as the right one, because at the half equivalence point, if pH equals pKa, if H plus equals Ka, because pH equals pKa, these two numbers have to be equal. And so in order for these two numbers to be equal, the concentrations need to be the same. The only one that has the concentrations of the weak acid and its conjugate base being the same is option B. And so those concentrations are greater than H plus because a weak acid does not ionize completely. So since the weak acid doesn't ionize completely, you're going to have more acid than H plus. And then all of those concentrations are greater than OH minus because as OH minus is getting added, it's being neutralized by the acid. So looking at a buffer, we looked at this example in class as to what happens when you add an acid or a base to a buffer. And so this gives the example of HF and NaF. So HF is the weak acid, F minus is the conjugate base. And so if you add a strong acid, then the basic part of the buffer is going to react with the strong acid in order to neutralize it. If you add a strong base, then the acidic part of the buffer is going to react with the strong base in order to neutralize it. And so that's why we have very similar pHs. It changes slightly, but not by very much at all. And the slight change is because when we use up part of the buffer, like in the case down here, if we use up some of the F minus to neutralize, we form a little bit of HF. Or if we use up the HF, we form a little bit of F minus, but not to where it's going to change the pH by 2 or 3 points. So then a weak acid HF is in solution with dissolved NaF if HCl is added, which ion will react with the extra hydrogen ions to keep the pH from changing. F minus, right, the conjugate base. So because we're adding we're adding limited amount of strong acid, the basic part of the buffer reacts with the acid. Neutralization is always acid plus base. Right? Neutralization always has to be an acid plus a base. So then going on to Ksp and solubility. So Ksp and solubility, remember Ksp is the solubility product constant. Ksp deals with dissolving a solid which is normally insoluble in water. We lied to you in Chem 1 when we said that things are insoluble because nothing is completely insoluble. Some things dissolve a very, very, very small amount, and that's what Ksp is based on. And so KSP, this example says what's the maximum number of moles of AgBr that will fully dissolve in 1 liter of water if the KSP value of silver bromide is 4 times 10 to the negative 12th. And so what you need to start with is if it asks you what the equation is for dissolving a solid in water, or the equation for reacting a solid in water. You don't actually have to show the water at all, but what you can do is show the AgBr solid at equilibrium with its ions. So AgBr solid is at equilibrium with Ag plus Br minus. And then remember when we did all the calculations with KSP, all we cared about was the equilibrium row. And so then what we looked at is if we are figuring out the moles of AgBr that will fully dissolve, I'm trying to figure out the amount of solid that I have at equilibrium. But remember, KSP, we're still using molarity. So we need to figure out what molarity of AgBr will dissolve. Well, what's my ratio of AgBr to Ag plus? It's 1 to 1. Now I can't plug in AgBr into my KSP expression. Why? Because it's a solid. So what we have to do instead is solve for Ag plus and Br minus and then compare that way. So if I have the KSP, which is 4 times 10 to the negative 12th, I can set that equal to x times x. My KSP expression will be KSP equals the concentration of Ag plus times the concentration of Br minus, and then I can just solve for x. And so if I take the square root of that, 2 times 10 to the negative 6th. Here's a quick shortcut for how I just did that. Because this could be right on the multiple choice test and you don't get a calculator. So I need to take the square root of x squared in order to just get x, which means I'm taking 4 times 10 to the negative 12th to the 1/2 power. And I can distribute this 1/2 to both. What's the square root of 4? 2. So I can take the square root of 4 and write my answer. And then if I have negative 12 and I have 1/2, multiply those together. Negative 6. And so 2 times negative 6, 2 times 10 to the negative 6 is my x. So that means that I have 2 times 10 to the negative 6 molar of both ions dissolved, which means that's how much silver bromide dissolved. But I don't want molarity, right? What's the problem asking for? So it's maximum number of moles, but how do I go from moles to, or molarity to moles? Multiply by volume, which in this case is 1. So it just so happens that my answer is actually going to be the same. And so 2 times 10 to the negative 6. So those are just some kind of tips and tricks for solving for things like KSP on the multiple choice part of the test. So then finding KSP from solubility data. So let's say that using a conductivity meter and a pH probe, a student determined the molar solubility. Molar solubility is how much solid you dissolve in water. Molar solubility is that number that we can put underneath the solid in the equilibrium equation. And it says which of the hydroxide salts above has the smallest KSP value. So there's one of two ways that we can go through and that we can solve this. We can solve the KSP for each. Right? Or, well, we're going to have to solve for the KSP for each. And here's why. If this small 3 right here was a 2, we could just look at our solubility data. But because it's a 3, that's going to affect our KSP calculations. Because if this, let's say that this 3 was a 2. That means that I have 1 positive ion and I have 2 negative ions of each. So I'm going to be solving for KSP the same way. And so since I would solve for KSP the same way, I can just see how much solid can I dissolve. Because if you think back, what does our value of KSP tell us? If I have a small KSP, remember that to solve for KSP, we look at the concentration of ions. If I have a small KSP, what does that mean about my my concentration of ions that I have at equilibrium? It's less, which means my solid does not dissolve much. So if I have a small Ksp, my solid does not dissolve very much. If I have a large Ksp, that means I have a lot of ions at equilibrium, and my solid will dissolve a lot. So that's kind of looking at what the value of Ksp means. So what we have to do in this case is we have to solve for Ksp for each one of these because our subscripts are not the same. And so to solve for Ksp for each, I'm going to just write out one of the equations so that I can show you, just to review writing your Ksp. So for barium hydroxide, which is a solid, and I know it's a solid because it tells me that we're determining the molar solubility of saturated solutions made by dissolving. So that means I have to dissolve these solids into water. So my molar solubility of barium hydroxide, they gave me as 0.11 molar. What's my ratio of barium hydroxide to Ba2+? 1 to 1, which means if I dissolve 0.11 molar, that means I dissolve 0.11 molar of barium 2+. But what's my ratio of barium hydroxide to OH minus? Right, so 1 to 2, which means I have 0.22 molar there. And so then what I can do is I can plug this into my Ksp. Always, 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 always write your Ksp expressions first, because Ksp is where people tend to forget the exponents the most. Because how will I write my Ksp expression? Ba2 plus times the concentration of OH minus squared. And then we can plug our numbers in and we can solve for Ksp. So then I can plug it in, 0.11 times 0.22 squared. That'll let me find Ksp. And I can go through all of that. And really what I'm going to notice is that it's really going to be between the chromium hydroxide and the tin 2 hydroxide. Because notice how small their solubilities are. They're much, much smaller than barium and calcium. So I'm really just going to focus on chromium and tin. And so what I'm going to do is I'm just going to write the Ksp expression for this, which is Cr3 plus times OH minus cubed. And then concentration of Sn2 plus times OH minus squared. Now if I'm going to plug in numbers for the chromium hydroxide, it's a 1-to-1 ratio. I have one solid, I have one chromium. And then what's going to be my hydroxide? So 3 times this much. And this is probably going to be one where you'd have to use a calculator, or they would give you numbers that you'd be able to work with a little bit more. But in this case, this one would be 3.9 times 10 to the negative 8th, because then you have to multiply those, and those aren't easy numbers to multiply. And then we can look at the tin. So 1.1 times 10 to the negative 9th times 2.2 times 10 to the negative 9th. Oh, look, and I forgot to do what I just warned everybody against. Don't forget to cube, right? Or square. And then you would work through and figure out which one of these KSPs is actually the smallest. And so when you solve, you actually find that the chromium hydroxide one is actually the least amount. And then this tells you if you solve without a calculator, Ba, Ca, and Sn all have the same KSP expression. And then it's between tin and chromium. And then if you just look at 10 to the negative 8th to the 4th power, so you have 3 of them here and 1 of them here, 10 to the negative 9th to the 3rd power, you can compare that way. Because if you have 10 to the negative 8th to the 4th power, you multiply them, that's to the negative 32. This would be to the negative 27, and negative 32 is less. Common ion effect, so just a couple more. Common ion effect can be affected by pH, So when we look at the common ion effect, this is where we're looking at the solubility of a salt and how it's affected by maybe temperature or pH. And so this gives an example of magnesium hydroxide. It's relatively insoluble in water. It has a Ksp of 5.6 times 10 to the negative 12. But when you add an acid to it, it actually changes the solubility. And that's because when you add an acid to any hydroxide, so this really just has to do with hydroxides when you're looking at the effects on pH, because hydroxides have that OH minus in it. And so when you add an acid, remember, acids and bases create neutralization reactions. So when you add an acid to this, you're actually removing part of this OH minus. Which then think about Le Chatelier's principle. This was already at equilibrium, and I'm taking OH minus away. I need to make more of it now. And if I need to make more of it, that means I need to dissolve more solid in to create more OH minus. And so this tells you as more acid is added, you start to dissolve more MgOH2 because that OH minus is being used up. But then you can look at how you can decrease solubility by using a common ion. So if you add MgCl2 to this, MgCl2 is a soluble ionic salt. Maybe you're looking at this being something MgNO3, because then that's one of the 4 solubility rules that you have to know, or maybe it tells you that MgCl2 is a soluble salt. When you add MgCl2, you're adding Mg2 plus ions and Cl minus ions. There's no Cl in here, so that doesn't matter, but you're adding Mg2 plus ions. So if you add more Mg2 plus ions to this system that's at equilibrium, now you have too much product, and so you're going to shift back to the reactants to use up that extra product. And so then that will, because you're making more solid now, you're decreasing the amount that's dissolved, and so you are decreasing solubility. So pH will increase solubility, common ion will decrease solubility. So for a solution that is equimolar in HCN and NaCN, which statement is false? This is an example of the common ion effect. H plus is larger than it would be if only the HCN was in solution. H plus is less than Cn minus, and NaOH will increase Cn minus and decrease HCN. So yes, this is a common ion effect. H plus is larger than it would be if only the HCN was in solution. Well, when you add NaCN, are you adding any more H plus? No, that one's actually the false one. H plus is less than Cn minus. That's true because if you are adding NaCN, you're adding Na plus and Cn minus. You're going to actually be adding more Cn minus there. If you add more NaOH, you are actually using up some of the H plus on the products, and you are going to cause more weak acid to dissociate. And then, so the last two, and I'll just kind of talk through the last 2 slides. The second to last slide talks about when you dissolve a salt in water. And so we talked about this when we talked about intermolecular forces. But when you dissolve something in water, when you form a solution, it depends all on the intermolecular forces between your solute and your solvent. Breaking bonds is always endothermic. Right? Breaking bonds is always endothermic. Forming bonds is always exothermic. And so really what it depends on is, are you breaking more bonds or are you forming more bonds? If you're breaking more bonds, then forming a solution will be endothermic. If you're forming more bonds, then it will be exothermic. When you form a solution, you are increasing disorder. When you form a solution, you are increasing disorder. And then finally, when it comes to favorability, you can relate energy and equilibrium by using delta G equals negative RTLN K. All right, that's on your equation sheet. When you're relating equilibrium and energy or spontaneity or thermodynamic favorability, you can relate energy and equilibrium using delta G equals negative RTLN K. If K is a really, really big number, your delta G will be very, very negative. If K is a pretty small number, then your delta G will be either not very negative or positive.